In this paper, we present a new deformation method which deforms meshes with enforced metric-based constraints. The algorithm of our method is based on a local global deformation strategy. We propose a scale-driven deformation method to deform the model locally or globally. The output model can approach the target metrics far better than the input model. Then a constrained optimization step is used to strengthen the accuracy of constraints. This is an example to demonstrate our algorithm. The input mesh is prescribed with 3 length constraints. It is deformed gradually in every step of iterations to approach the target constraints. It is easy to notice that the output of each step approaches the targets better than the last step. After the iterative scale-driven deformation is finished, we perform a constrained optimization step to ensure the accuracy of all specified metrics. Usually we cannot apply constrained optimization directly on the input model if target constraints differ greatly from the input. Direct constrained optimization cannot generate well-shaped results. Increasing the target gradually in each iteration cannot ensure good results in shape and detail preservation either. In this example, the lengths are increased by 20% by applying constrained optimization in each step. In our deformation framework, we first use iterative scale-driven deformation to scale the input model locally or globally. The output model can approximate the target constraints far better than the input. Then we perform a constrained optimization step to ensure that all target metrics can be satisfied as accurate as possible. 3 types of constraints are defined in our framework. For length constraint, user can define open or closed curves on the input model and set different target length for different curves. For area constraint, user can select an patch and modify the area of the selected patch. In our framework, we are able to modify or preserve the local volume of parts of the model or the whole volume of the input mesh. In this example, we show a volume-preserved deformation of the starfish with length and area constraints. Our method can be used as an user-friendly tool to edit and modify models. It is very easy to add metric-based constraints on the model with different target values. The results can be generated effectively and efficiently. In this example, we increase the selected area on top while fixing the area of bottom. It is easy to notice that the sharp features are preserved on the deformed results. With this example, we also show in comparison with another method ShapeUp. The top area are doubled in both results. It is easy to notice that our method gives better results in preserving the details and smoothness of the input model. We can define different combination of length, area, and volume constraints on different models. Different constraint combinations can generate various deformation results. When intersection of constraints happens, our method can still deal with the constraints and deform the mesh to satisfy all the target values. In costume designing, tight or loose clothes or trousers are often expected in many designs for aesthetic or functional purpose. Based on an input human model of user, designers need to modify the input model first to make it suitable for designing clothes. Our method provides a way to control the design of clothes on body by adding hard length constraints on the key feature curves of the input model. The deformed model from our method can be used as the new human model for designing. The patterns of clothes can be obtained by flattening the 3D mesh pieces generated from the deformed human body. We also show the comparison of 4 selected 2D patterns.